Let's see, test, test, test. You got audio. So I think we are good. And yeah, so welcome to class. This is the kickoff of the circuits class, Engineering 12. Ready to dive in again. Kind of like statics, only harder. This is harder than statics, yes. More harder. Harder and more harder. And this is the Canvas site, and if you were paying close attention, you'll have noticed I kicked off the video by clicking on this link, which I'm recommending if anybody wants. If you're stuck at home ever, and you want to say, "Oh, I'd like to kind of check in on the lecture in real time," at 1 o'clock, you can click on this link, and it will open up a portal into this computer, so you can watch and ask questions and all that stuff remotely from home. And these lectures will show on the playlist here on YouTube. There's a few handouts. You can watch these later on YouTube, so I'm expecting online folks to pull down the stuff that way. Here is the playlist. Right now there's nothing there, but there will be. So this is Canvas. It's the place where all the material will be from. You've got my contact information here. Also have online office hours, Sundays from 8 to 9. Again, this is especially for online students, but anybody working at home can tap into these from 8 to 9 p.m. And again, you just click on this link. It's actually the same link as that, but I just put a separate thing there so people wouldn't have to guess. This is the link. You click on that, you'll be connected to me Sunday nights from 8 to 9. The homework is due on Sunday nights or Monday first start of class, so that's a good time to get help. If you are stuck on anything, just tap in and ask questions. We can get you through this stuff. It's a challenging class, but it's all very, of course, very logical and stuff. You just have to kind of practice. And we are going to start. I guess I got to start with the syllabus, don't I? So here is the link to the syllabus. I'm going to move this thing somewhere else. Move to the bottom. All right, move to the bottom. Well, that's no good. And move to the side. Hate this thing. Dock to top. All right. I guess I can temporarily move it to the bottom and then do what I need to do. Anyway, so here's the syllabus and what to say here. They may have updated the edition. I have, basically I'm taking, so when I provide the homework, I'm providing the homework from the 4th edition, and I'm providing today. So you can grab the problems right there. If you don't have the 4th edition, you can still function with the other editions. Just make sure you look at those homeworks that I'll be posting up there. And yeah, so basically, we're learning all different techniques of circuit analysis in this class. This class is a prerequisite for almost all of the engineering majors. If you're mechanical, electrical, aerospace, civil often need it, but some some programs don't require circuits, but it's a very useful class. Is anybody in a different major than the big three: civil, mechanical, electrical? Yeah, what were you? Physics. Oh, yeah, it's a great subject for physics, of course. And there are physics, like I had a student who took circuits here, but then he had to take it at UCSB again because he was a physics major. Yeah, so you might have a little different flavor in circuits, but you'll learn a lot, so it'll help you. Cool. There is a lot of homework, and the standard pattern for solving problems is to write out the problem statement and what you're supposed to find, and then develop your solution using diagrams, sketches, circuit diagrams, and things to intermediate steps and all that stuff. And you want to be as neat as you can because that encourages clear thinking. The course involves homework, quizzes, tests, 4 tests, 4 one-hour tests, and a final exam. The homework and the quizzes are 12%. I don't know why it's broken up that way. It's basically 4% for quizzes, 8% for homework, and 60% for all 4 tests. So that's 15% for each test, and then 28% for the final exam. So it really pays to do the homework. Doing the homework prepares you to take the quizzes, and then the quizzes prepare you for the exams and all that stuff. So these are the topics we'll be covering. You've all learned in physics, like up to about Kirchhoff's rules, I think, maybe series and parallel. So the first week or 2 should be fairly familiar. And then we'll be looking at more advanced techniques, nodal, mesh analysis, superposition, and working with different circuit components. Eventually we get into like op amps, and then we look at inductors and capacitors, really fun stuff. And alongside all these things is the circuit lab class, which we will be kicking off tomorrow. And I'll have more information on that, but we will be working with a lot of these ideas with physical hardware, so you'll get to have a sense of what this actually means, which is really valuable. So when you come out of the class, you'll have a confidence of working with circuits and understanding. Will really help you in your future studies. Unfortunately, I've copied something from another class, so this is Engineering 4. But basically what I want you to do when you send me an email, if it's for circuits, because people don't realize I teach a lot of classes, so if you just send me an email like, hey, when is the homework due? I have to go ask you, what class are you in first? So just tell me in the subject line what class you're in. That would be really helpful. There is a drop date for the class, and that's typically like the first week of May or so. Make sure you stay on top of that in case you do need to drop. After drop date, it's really difficult to get out of a class if you forgot to drop. So you end up getting stuck getting a grade. You can get an incomplete if you've accomplished 75% of the course material and some emergency happens in the last month. But the registrar is very hard-nosed about giving incompletes. They will often refuse to honor an incomplete that I would like to give sometimes, just because of their policy. So make sure if you do need to drop, go ahead and drop. If you have any accommodations, please let me know. There are also, if you need extended testing time, there is a way of getting that in our Access Resource Center. And then there's a whole thing on plagiarism, academic honesty, things that everybody should know, but sometimes they forget in the heat of the moment. So please review that and follow the high road whenever possible. Any questions? Okay. then we can get started with some actual circuits lecture stuff. And again, to kind of show you a little bit more around the course Canvas site. If you do need a little bit of explanation of how Canvas works, you can check out this link here. In fact, I can just click on this. One thing that you might want to do, I'll tell you, one of the real heartbreaks is when I like post an announcement about a test or something, and then like someone comes in and goes, "Oh, there's a test today? I didn't know that." Because if you're not getting the announcements, you know, you might be surprised by things like that. So there are ways of making sure that you get notifications. Like you can sign up to make sure that notifications come via text message for you, or you can add an additional email. If you don't check your MPC email account regularly, then you should add another email so that you do get the announcements. Because I'm going to be posting announcements to this class. I've already posted some announcements, and this is just really, really good for you to do that. So here is the announcements so far. The starting instructions. Did you all get that email that I sent out? Now I sent that out to the email that I have from your registration, which is different than Canvas. Canvas announcements only go to your npc.edu email. So if you want to get those announcements, you want to make sure that you either forward your NPC email to your personal email, or you check your email all the time, or you put in an extra email in Canvas so that it's sent. So that's something you're going to need to do on your own. That's really important for you. And then each week, it basically lists the assignments. Quiz 1 is already going to be next, what is that, next Wednesday or something? It's February, no, I guess. When is February 4th? Next Sunday, week from Sunday. So, also, by the way, so the quizzes are just, they are like where so much learning goes. The quizzes are actually quiz questions I grabbed from San Jose State's circuits test bank that they used to have posted available publicly, but they've now hidden behind some other login walls, so you can't see that anymore. But I grabbed all of their questions. They have like a 300 question test bank. Is anyone going to San Jose State? No one's planning to go to San Jose State? Okay. Well, this is maybe a surprise, but what's interesting is circuits is such a hard class that even the students who take circuits at San Jose State, they have to take another class after that called like circuits problem solving to make sure they really learned it. And everybody has to register, even their students, as you know. So if you come in and transfer, you have to register for that as well after you take circuits. And I think it's like I think it's just maybe a 1-unit class, but it goes the whole semester and just has you solving circuit problems over and over again. Well, if you really learn circuits, you can take a challenge test and you can take a challenge test and you still have to enroll in the class, but you don't have to sit in it. You don't have to do all the work. So, and that challenge test had they have this test bank of 300 questions there. And that's what I grabbed and made all the quiz questions for this whole class. So every other week there's a quiz. And before you take the quiz, you can take the quiz you can take the quiz review. And you can take the quiz review any number of times you want. Now the quiz actually is all done using what's called formula questions, meaning everybody gets different numbers on the problems. So you can't like ask your friend what's the answer to number 1. And also you're going to be selecting from a quiz bank, so you're not going to all have the same problems even. So you're going to have to all figure this out with your own numbers, okay? And you know, well, actually, what I sort of recommend, well, if you think you know it, you can just go ahead and take the quiz. I think you can take each quiz twice. So you could take it once. If you don't like your score, then I would kind of go do the review quiz so that you really learn it, and then you can take the actual quiz a second time. Isaac. It's up to you. You can do the review quiz before you take the quiz. Yeah, but I think you can take each quiz twice, and your highest score will be applied. The review quizzes don't give you any points, but you can take it unlimited number of times. So you really, because people can fake their way through these things, and give partial credit on tests, but the quizzes are going to kill you if you don't really know this stuff. You really got to practice with these. And the quizzes are actually setting up for the final exam, which is, guess where that's from? It's the same test bank. So all these quiz questions are actually practice questions that might appear on the actual final exam, which is multiple choice with different numbers than what you've seen. So it's really, you got to learn how to solve these problems, and you got to practice so that it's all automatic and it comes real easy for you. Okay, there's no way out. You got to learn it, and it's fun. I think since I implemented this, the learning has just improved so much because you can just practice over and over again. Right? That's really what people need, is just practice. And this is what the quizzes let you do. They're just going to really help you practice over and over. Anyway, so here is assignment 1, and each assignment has the lecture that goes with it, so you can pull up these slides. And if you click on the annotated slides, you'll get the marked up slides. So like if you just want to see how, refresh that. Like if you just want to see how problems are solved, for instance, you can pull up these annotated slides. Here's a problem statement, and you might have a homework problem that's similar to one of these in the lecture, right? So you can read these as practice problems for the homework. You can read a similar problem and follow those steps and then do your homework problems the same way, right? That's why this is all there. Now, we're going to do these problems in lecture as well, and that is what this link is the lecture without the annotation. And so what I do in lecture is I have the annotated slides here on my instructor, and then in PowerPoint, we just go through and do this. Now you have the handout of the non-annotated slides as well, so we go through and you can mark up those with problem-solving steps as well. So this is all very well organized, and it's all going to help you learn this stuff. So we've done everything here, kind of showed you, this is a specific Canvas, by the way. And there's a guest book survey. Did you all fill out that survey? It was in the email that I sent. So please fill that out. Check your email again and just provide that. It really helps me. We're doing program review this semester, this year, I think. Just kind of get a feel for, I really like to know like who's taking the class and where they're planning to go. So all that stuff is really helpful for me. And we'll be doing a concept inventory tomorrow, which is just a kind of way for you to kind of see how much you actually know from circuits from your previous exposure, like in physics. Does anyone have any questions before we start the actual presentation? Anything about the class or anything? I covered it all so well, right? Okay. Yeah. That's a good question. Is it really important to get the book as a hard copy, or is a PDF okay? So you're an engineer, right? Okay. Now what I tell people is this investment in your education is what you're going to be making your money off of for the rest of your career, or at least until you do something besides engineering. And people can often, I provide a lot of support. People say, well, I don't really need the textbook, right? And they can blow their way through the class without the textbook, maybe, right? Okay, great, you saved yourself some money. All right, next year you're at like San Jose State or some other place, and you're doing a class that kind of follows on from circuits, and you gotta go like figure out a circuit problem again. How are you gonna do it? You wanna look at a PDF? I don't know, maybe, but the easiest way to find stuff I like is just books, hard copy books, right? It's the best. And I get people emailing me, hey, I've transferred, and I've got to review circuits again. Can you send me the link to your lectures, because they were really helpful for me? And I'm like, dude, get a book. Yeah, you can download them if you want and take them with you, but they're really not that good because there's no explanation, right? Eventually, you're going to really need to read stuff as an engineer. That's what you do all the time. They pay you because you can read those things, right? And circuits is one of those things. It's like so important for so many things in engineering. You should get a book. I answered that longer than I should have, but I do. I run into that a lot, and it's really. I think people kind of shortchange those. Now the book, because you don't have to have the 4th edition. You can get the 3rd edition. It's not that expensive. You can buy a used copy of the 3rd edition for probably $20 or less. So, and these are really valuable books, just really put together really well. So I really recommend getting a book. I still have my books from 30-some years ago. Yeah.
If you have a newer version of the book, like the homework problems, will they still have that?
No. Yeah. But the homework problems are all posted here. Right. They're all posted on the website. And you can get the 4th edition. Yeah, you can get the 4th edition. Yeah. Ready?
The online link on WebReg is to the 6th edition.
Yeah, because the 4th is out of print. But I'm not going to update all the homework and solutions and everything. Yeah, so we're doing homework from the 4th edition. Yeah, you can have whatever edition you want. Yeah. So anyway, yeah, so what we're learning is a bunch of principles and techniques for predicting circuit behavior. And a circuit is a connection of electrical elements that manipulates electrical energy. This is all very abstract stuff. This is why circuits is harder than statics, because like, what did that just say? Right? We're manipulating energy, and what we do, we can use things like amplify sound. You can create signal. You can modulate sound onto higher frequency radio waves and send them out into space or across the country. You can have other circuits that detect all that stuff and convert it back. So that's, and then there's the whole power systems, transmitting power, another big part of circuits. So that's what we're learning. And the understanding of how current and voltage works, just getting an intuition of these things, just super, super important. And that's really what we're striving for in this class. So the system of units and what quantities working with. Well, we don't do too much with length, mass. We're going to use time. We're going to work with charges, units of charge in coulombs. You have positive or negative charges. Temperature. We're not working with temperature. We're not really even working with luminous intensity, although you can make circuits that kind of work with optical stuff. We are going to be working with some photoresistors, which will be sensitive to luminous energy. We're not going to be measuring it or using it. But we do use some of these these prefixes because the quantities in circuits can range over very large values, very large ranges, very many decades. And so you have to know all these prefixes and things as well. We go through these. And then, of course, these derived quantities come from the basic quantities. We're not really working with these guys. We're not really working with forces. That's more statics. We are going to work with work and energy, power, current, and voltages. And it's telling you what these things are. A watt is a joule per second. That's an energy flow of 1 joule, you kind of flowing into or out of something per second. Current is the rate of flow of charges, so the unit is coulombs per second. Voltages are this mysterious thing, but it's how much energy we're actually adding to the charges, so or taking away. So that's what a voltage is. The forces involved in circuits are the electrostatic forces. So yeah, these are units of newtons, but this is really more the world of physics, and we're not going to really spend any time at all in this world here. But I mean, they showed you all this in physics. It's the basis of circuits, but circuits is sort of another overlay on top of this world. But if you have two charges, separated by some distance r, you can calculate the force between them, either an attractive force or repulsive force. But again, we don't really care about this in circuits. Electrodynamic forces due to charges in motion. Yeah, electrical engineers would find this useful, maybe for certain things working with fields and stuff. And the formula, you might have gotten this: force equals the charge and u cross b, where u is like the direction of the velocity of the charges. And it's fascinating stuff, right? I was really, I love working with fields. They're just so mysterious, right? But if you have a magnetic B field, and this is the magnetic field, right? And you've got some charge Q going off in this direction, then it's a cross product. It's a cross product of U crossed with B, meaning the force on that charge is going to be which way? Into the page, right? Yeah. So the force on that thing is going to be going this way. We're not doing this either. So this is all, from Physics 3B. This is kind of preparatory material, and doesn't really concern us in circuits. What does concern us is the flow of charges. This is actually where stuff happens that we're interested in circuit work. And the flow of charges is the amount of charge passing through a cross-sectional area of some conductor per unit time. And what that means is, if you think of a wire as a tube, and the charges are migrating through that tube, and it has a cross-sectional area, right? And let's see here. Well, what do you got here? You got some area, and you've got some cross-sectional area. You've got some, vector of charge flow. This is all very messy, but you've got some flow of charge here, right? So, and here's I, and it's E, which is the charge on electron, and then the number of electrons times the cross-sectional area and the velocity there. So it is this thing. Again, this is sort of the physics of charge flow. Again, we're not really that interested in that, but basically, if you take some AU delta T, that sort of gives you the total charge. So the number of electrons, it gives you a sort of integrating how many charges. That's your N. That goes over here. Sorry. Yeah. Good question. Yeah, this is physics. We're not doing this. Yeah, for edification. Well, let's see here. NE is the number of electrons. Here we go. NE is the number of electrons per volume. So that's like a density. E itself has a value. That's the charge on an electron it's 1.6 times 10 to the minus 2, 19, 2, 19, 10 to the minus 19 coulombs. And the amount of charge passing through a given cross-sectional area of the conductor per unit time. And what really is sort of happening is when you have charge, you've got like, if you're counting how many charges are going by in a certain amount of time, that's actually telling you the current. So in other words, if you've got so many charges, it's really the number of charges per second, right? That's what current is. So the dq is like, if you're counting how many charges are going by here, dq is like how many charges have changed. What's the change in charges? You're counting, it's like if you're counting cars on a freeway, you know how they have these rubber strips across the road sometimes, right? What are they doing? Well, they're counting every time like a tire goes over there, kind of count. They can figure out how many cars are going by. And if you're counting, if you're taking track of that count over time, that count gets bigger and bigger and bigger, right? And if you sort of plot this thing, let's just sort of do a graphical interpretation. If you plot charges versus time going through, say, this point here in the wire, right? You're going to see, oh, these charges are getting bigger and bigger and bigger, right? Well, at a certain point, you can just say, well, let's just figure out what's the rate of that line there, right? And that's dq over dt. And you could do it over a small interval, where this becomes a dt, and this distance here becomes a dq, or you can do it over a large interval, like a delta q over delta t. And if the current is constant, you're going to get the same rate, right? So basically, I is the slope. Right, q of t. So that's a better conceptual understanding. This is the sort of the physical underpinnings of all this stuff, and I didn't answer your question. I know. I can't tell you. This is physics. We're not doing physics. Okay. Yeah. You want me to look it up for you? I can get back to you tomorrow. Yeah. Okay. Well, what's interesting about charges, and this is where it can get confusing, and this is actually one of the most common mistakes people make in circuits, is sign errors, because they forget about, oh, the sign's going this way or that way. Well, they don't forget about it. If you do the math carefully, it will all kind of come out okay. But there are some points where you kind of have to make a judgment over whether like power is flowing into or out of something, or charge is going one way or the other. And the understanding of charges took place before people really understood what the atomic model was all about. And so they assigned a notion of charge to what was, they considered the flow of positive charges. And so what we sort of think about with current is the flow of positive charges. So if you imagine a bunch of positive charges flowing to the left, we think of that current as flowing to the left. In reality, it's the electrons in most cases that are flowing. And when we have positive charge flowing to the left, in fact, electrons are flowing to the right. And but this is still considered a current that's flowing to the left, because it's negative charges that are flowing to the right. It's sort of the same thing as positive charges that are flowing to the left. That makes sense? Yeah, like that, I know. It just adds a whole extra layer of doubt on everything you do in circuits. Just that one stupid thing. And I think it was Ben, I don't know, it was like Ben Franklin that did it. Does anybody know who came up with that? Some of the people whose early experiments with electricity, they kind of just decided to kind of, call charges a certain way, and they sort of chose the one that wasn't actually traveling. Isaac? 75% you understand what I said. All right.
Why is it flowing to the left?
why is it flowing to the left if there's a negative charge going to the right? Yeah, because current, the definition for current is the direction of positive charge. Because we know that negative charges going to the right, we can assume that positive charges are going in the other direction. In a way, yes. It's sort of a mental model, just, yeah. And, you know, one way that people can kind of, one way to kind of help, I don't know if this helps or not, but there's often, when you get into like higher electrical engineering classes, they'll talk about, instead of the flow of electrons, they'll talk about the flow of holes. And when you're talking about like a crystal metal structure, what's happening in wires like a metal crystal, and electrons are just sort of hopping from one atom to the other in a certain direction, right? And well, how does that hopping actually take place? Well, if you think about, if you sort of draw the atoms here, and let's just, yeah, let's just, you know, we could sort of shade in the ones that have electrons, and we can leave empty ones that might be missing an electron, right? There's an absence of an electron that's like a hole. And if an electron jumps, like, say, from here to here, right? Now this guy's shaded, right? But this guy's now not shaded. Oops. So, like, the electron moved to the right, but which way did the hole move? To the left. See what I'm saying? Right. So the electrons will move to the right, but the holes will move to the left. Holes are kind of positively charged because an absence of electron means you have sort of a net positive charge. So the migration of these holes to the left follows the migration of electrons to the right. Okay, another way to think about that. Better? Yeah. Yeah, they're basically mental models of what's happening. I mean, we don't actually usually have positive ions traveling, although you could have that in a liquid. You know, you can have positive ions flowing one way or another. But it's more like in a wire, it's more like these holes kind of flowing in the opposite direction of the electrons. The convention in circuits is to think of these holes traveling, the direction of these positive charges traveling, these imaginary positive charges traveling. Yeah, even though it's the electrons that are traveling. And you just get so used to that, you forget about the fact that there's electrons go in the opposite direction of what you're just thinking. You just get used to it, but it takes a while to get comfortable with that. So an example problem. Total charge entering a terminal is given to be Q equals 5t sine 4 pi t millicoulombs. Calculate the current at t equals 0.5 seconds. Okay, so the total charge, that means we're actually counting charges, okay? Could be electrons, could be these holes, whatever. And you've got some circuit element. And you've got some charges flowing into that element, right? And it's entering a terminal, and here's your terminal. And Q is just this sinusoidal curve. It's 5t sine of 4 pi t, which, I don't know, you can sort of imagine, what is that? That's a sine wave multiplied by what? A line like a ramp, right? So how do you visualize that? What do you see when you think about what that looks like? It's a sine wave that kind of starts off really small, right? and then kind of gets bigger and bigger and bigger, right? Yep. Would you have to multiply the equation by 1,000 to turn it into coulombs? Or just leave it in millicoulombs? I would just leave it in millicoulombs for now. And I don't think you want it, you would divide it by 1,000, put it in coulombs, not multiply by 1,000. So the slope of this thing is 5t, right? And then this is your sine 4 pi t multiplying that. And at some time t equals 0.5 seconds, we're trying to figure out what the current is. How are we going to figure that out? What's the formula say about current? dq dt, right? So we have to take the derivative of that curve at time 0.5 seconds. Right? We have to do a little calculus to kind of find the answer. So I'm going to give myself a little room and erase this. So given so here's the way we solve these, right? Given q equals 5t sine 4 pi t millicoulombs, we have to find I at t equals 0.5 seconds. So I of t is dq dt, slope, and it's going to be the derivative of 5t sine 4 pi t. And you know how you derive these? This is what is this? The multiplication rule or something? What do you call it? The product rule, right? Yeah. So 5 sine. So it takes you take the derivative of this guy times that. So 5 sine 4 pi t plus. Then you take 5t and then take the derivative of sine 4 pi t, which is going to be cosine of 4 pi t times 4 pi. And that means I at t equals 0.5 seconds is going to equal, well, you plug in 0.5 to this, and this, and that'll give you 31.42 milliamps. Okay, questions? So example 2 is talking about, well, now we've got current flowing through an element. And if we want to know what the total charge is entering the element from 0 to 2 seconds, how are we going to figure that out? So we are given our I of t is this sort of piecewise defined curve. We have to find q of t. Okay, well, how are we going to do that? Sorry? Yep.
Coulomb per second is amp.
Coulomb per second is an amp. Yep. Yep. Good question. Yeah, so this is, right, we're doing dq dt, so the units of that's going to be millicoulombs per second, which is a milliampere. Okay, so what's the trick to solving this one? Mark? Got to integrate the current, right? We're given the current is this piecewise thing, and we can sketch this thing out. So here's the current. It's 2 amps initially. So maybe this is 1 and this is 2. And it's sitting here at 2 amps, and then at 1, it becomes 2t squared, right? So at t equals 1, it's still 2, but then at t equals 2, it's going to go up to 8, right? So it's going to do something like that as a parabola, or this is going to be 8. And we have to integrate this thing, right? We got to find the area under here to find the total charge, because what this is saying is the current is a flow of charges, and we've got to figure out, if we want to find how many charges there are, we got to integrate that flow. So we have that region here, and then we got to also integrate this region here. And that's going to be the total charge. Right, because we recall the formula said I equals dq dt. And that means q of t equals the integral of I dt plus c, some constant c. And maybe there's some initial charge in the element at t equals 0. That would be some q of 0, constant. So all we have to do is say, all right, so q of t, and yeah, there's going to be some constant here, but I actually think of this more as a definite integral, right? So in other words, we can say q of t is going to be the integral from 0 to 1 of 2, right? Because that's I dt, right? Plus the integral from 1 to 2 of 2t squared. Right? It's a definite integral because you've got definite limits there, right? You really want to know what's the current flowing from 0 to 2. And there's 2 different mathematical formulas for that, region. So you got the flat part, and then you got the parabolic part. So you're just going to integrate those 2 different regions separately using those limits, and then you just add them together to find the total. Actually, this shouldn't say q of t. This should say q of 0 to 2. Total charge from 0 to 2 is that. So that equals 2t from 0 to 1, and what is that? 2t cubed over 3 from 1 to 2. So that equals 2 plus, this is going to be, looks like 8/3 minus 2/3. So that should give us, because I got a 1 here. Right, in that limit, Because we're finding the area from 1 to 2, right? That's this thing right here.
A minus 7. A minus 1 is 7. I'm having a 2, right? A third minus 2 thirds.
Oh, wait, it's 16 thirds, right? I messed up. It's 16 thirds minus 2 thirds, right? 16 thirds minus 2 thirds, don't you agree? Because when you plug in a 2 there, that turns that into 8 times 2 is 16, 16 over 3, right? And then you got to subtract out a 1 there, so you got 2 times 1. So 16 thirds minus 2 thirds, so that's going to be 2 plus 14 thirds. Fourteen thirds is what? 4.666, right? So the whole thing is going to be 6.66. And the units are coulombs. Good. Question?
Will you always prefer decimals or fractions?
Well, I always prefer decimals over fractions. Yeah. Yeah, it's kind of funny. In math, they sort of train you to put like fractions, reduce things fractionally and stuff. And it just doesn't work in engineering, right? Did you ever go to like Home Depot and ask, I need a board that's 3 5/8 feet long or something? No. You have to know what it is in decimals. Well, actually, I don't know. Feet. When I'm looking at your answers, I appreciate decimal value. Yeah, your voltmeter is not going to give you fractions. So that is it. If you can stick around, I forgot to do attendance. Actually, it's here. Okay, so we should have Mason here. Yeah. Sebney's here. Omar. Ali's here. Mark's here. Isaac's here. Cameron. Matthew. Alexander. Okay. David. Daniel. Hong. Okay. And is anybody here from the online section? Francisco, Andrew, Miguel? No? Okay. Anyone I didn't call? Okay. Well, so tomorrow we're going to be meeting in, I think we're in PS 107 for Circuits Lab. In 107, yeah. We have materials tonight, yes. We do have someone who's going to be doing the lectures, or they're actually not lectures, they're problem sessions. The lectures are online. Yeah. Mm-hmm. Did you take Circuit? Oh yeah, you started before. Yeah, you took it before, yeah. Yeah. What year did you take it? Was it 2016?
2016.
Yeah, okay.
I was taking it Devin. Devin was taking it. I actually left in the middle of the first lab.
Okay.
Yeah. You had to finish it playing song. He was cursing me all the time.
The first lab? That's a fun lab.
Yeah, it's this thing.
Yeah, yeah. The rubber band one and those metal rods. Yeah.
Yeah, we used to hang.
Yeah, with weights. Yeah, those are fun.
We don't have a lab today though.
Sorry.
Lab for
Today?
No,
It's Friday.
yeah, it's right.
Materials lab is Friday, yeah. Our lab for this class, circuits lab, is tomorrow. It was like Friday or Saturday or something like that. Okay. Well, no, but I posted as an announcement on Canvas. So when you get into Canvas, you can just read that announcement. Yeah, the link to the form is there. Yeah. Mm-hmm. Yeah.